We know that the work done by an external force to bring a charge Q0 from infinity to a point in the electric field of any charge distribution is equal to the electrostatic potential energy of the charge Q0 at that point. That is, the work done to bring the charge Q0 from point S at infinity to P is equal to the potential energy of Q0 at point P. Since the force on charge Q0 due to any static charge configuration is F equal to Q0 E, the work done will be proportional to Q0. We can say that W is equal to a constant K into Q0, or the quantity W by Q0 is equal to K. Therefore, the resultant quantity obtained is independent of Q0. The work done per unit test charge is a characteristic of the electric field at that point due to the charge configuration and is known as electric potential at that point in the electric field due to the charge configuration. The electric potential is denoted by V. Let us consider a point P between the origin and point S. Then, potential energy of the charge Q0 at points S and P is US and UP respectively. We know that the work done by the external force to bring charge Q0 from point S to P is expressed as WSP is equal to delta U, which is equal to UP minus US. If Vp and Vs denote the electric potentials at points P and S respectively, then the work done by the external force to bring the unit positive charge from S to P is equal to Vp minus Vs, which is in turn is equal to UP minus US by Q0. Choosing S to be at infinity and also the electric potential at infinity as 0, the work done by the external force to bring the unit positive charge from infinity to point P in the electric field is equal to the electric potential Vp at point P. The electric potential V at any point in the electric field of a charge configuration is equal to the work done to bring a unit positive charge from infinity to that point in the electric field. Let us obtain an expression for the electric potential V at a point in the electric field of a point charge Q at the origin using the definition of the electric potential V at a point in the electric field of a static charge configuration. Consider the electric field of charge Q, in which P is a point at distance r from it. Consider the point S in the electric field, which is at distance r' from the charge Q. Let a unit positive charge Q0 with a charge of +1 coulomb be placed at point S. The electrostatic force Fe between Q and a unit positive charge placed at S will be equal to 1 by 4 pi epsilon naught into Q into 1 by r' square into r' cap, where r' cap is the unit vector along the direction of OS. Therefore, Fe will be equal to 1 by 4 pi epsilon naught into Q by r' square into r' cap. Let this be equation 1. Now let us move the unit positive charge from S towards P in the electric field by a small distance dr'. and let dW be the work done in the process. The external force F required to move the unit positive charge is equal and opposite to the electrostatic force Fe. dW will be equal to F dot dr dash, which is equal to -1 by 4 pi epsilon naught q by r dash square into dr dash. Let this be equation 2. We observe from equation 2 that the value of dW is negative, since charge Q0 is moved against the direction of the electric field. Now let us assume that the unit positive charge is brought from infinity to point P in the electric field. And let work W be done for this process. Then W is equal to integral dW. Let this be equation 3. Substituting the value of dW, we get W is equal to minus integral 1 by 4 pi epsilon naught q by r dash square into dr dash in the limits ranging from infinity to r. Let this be equation 4. Since 1 by 4 pi epsilon naught q are constants, and evaluating only the integral, we have integral 1 by r dash square dr dash in the limits infinity to r is equal to -1 by r dash in the limits infinity to r, which is equal to 1 by r minus 1 by infinity. On further simplifying, we get W is equal to 1 by 4 pi epsilon naught q by r. Let this be equation 5. This is the expression for the work done to bring a unit positive charge from infinity to r, which is equal to the electric potential V at point P. Therefore, the electric potential V at point P is equal to 1 by 4 pi epsilon naught q by r, which is the expression for electric potential at P in the electric field of the point charge Q. Let this be equation 6. The electric potential V is a scalar quantity, and its SI unit is joule per coulomb or volt. 1 joule per coulomb is equal to 1 volt. We know that the electric field E of a point charge Q at a distance r from it is inversely proportional to the square of the distance r from it. The graph shows the variation of electric field E with respect to r. The electric potential V at a point in the electric field of a point charge is inversely proportional to the distance r from the charge as seen earlier. The graph shows the variation of the electric potential V with respect to distance r from the charge. The electric potential V at a point in the electric field can be positive or negative. This can be understood from the following solved examples. A point charge of 1 microcoulomb exists in air. Find the electric potential due to the charge at a distance of 10 centimeters from the point charge. Given that charge Q equal to 1 microcoulomb equal to 1 into 10 raised to the power minus 6 coulomb. Distance from the charge is r equal to 10 centimeter equal to 0.1 meter. The electric potential due to the point charge at distance r from it can be calculated using the formula V is equal to 1 by 4 pi epsilon naught into Q by r. The value of 1 by 4 pi epsilon naught is equal to 9 into 10 raised to the power 9. Substituting the values and calculating for V, we get electric potential V due to the charge at distance r equal to 9 into 10 raised to the power 4 volts. Solved example 2. Two charges, 2 microcoulomb and -4 microcoulomb, are separated by a distance of 20 cm in air. Find the electric potential at the midpoint of the line joining the two charges. Solution. Given charge Q1 is equal to 2 microcoulomb equal to 2 into 10 raised to the power -6 coulomb. Charge Q2 is equal to -4 microcoulomb equal to -4 into 10 raised to the power -6 coulomb. The distance of the midpoint from Q1 as well as Q2 is equal to r is equal to 10 cm is equal to 0.1 meter. At the midpoint of the line joining the charges, the potential is V is equal to 1 by 4 pi epsilon naught into Q1 by r plus Q2 by r. Substituting the values of the various given quantities and simplifying, we get V is equal to -18 into 10 power 4 volt.